theta such that the posterior probability of theta is maximized based on the base formula, right? So if I want to expand it, it becomes f of x condition on theta times f of theta over f of x based on the base formula, right? So we know that this f of theta is the prior, it's called priory. What is the meaning of this priory? It means the prior knowledge about the underlying parameter you have. So this is your prior knowledge. Prior knowledge about theta. What about this one? This one was likelihood, right? So in MAP, you are trying to find the best theta such that the posterior probability is maximized, right? What about the other one, LMS, least mean square? For these means where you are trying to find the best value for theta such that the expected value of, we call it theta hat, the expected value of theta minus theta hat to the power of 2 condition on your observation is minimized. Arc mean, sorry. It turns out the answer for the solution for this was equal to theta hat equal to expected value of theta condition on x. There's a common thing between MAP and LMS. For both of them, you need f of theta. So obviously for finding MAP, you need to use base formula. And this f of theta shows up here. But what about this one? For this one, I know that I need to find the integral of theta times f of theta condition on x, the posterior probability. For finding the posterior probability, we go back to the formula. Still, you need to use the f of theta. So here's the point. The point is that both MAP and LMS use f of theta. This is important. But what about the other one? The third one, which is likelihood estimator. For the likelihood, as its name suggests, we only care about this part. We are trying to find a theta hat such that this term is maximum, the likelihood, f of x condition on theta. This is what likelihood does. So we only care about this part. So the good thing about likelihood is that you no longer need f of theta. That's the point. So if you see a question, f of theta is given, you most likely need to use one of these approaches. Otherwise, the only option you have is MLE. So the third one is MLE. I forgot to write the name. Minimum least square. Maximum likelihood estimation. Yeah. Maximum likelihood estimation. So that's the difference between them. Okay? Okay, but how can we find MLE? So what if so here I only had one observation. What if I have observations observations. I don't know what's wrong with this marker. Observations x1, x2, up to xn. Then in this case, you need to maximize f of x1, x2, up to xn conditional here for the likelihood. Because for the MLE method, you are trying to maximize the likelihood. If you have n observations, this is the formula for the likelihood, right? But in general, finding the joint distribution of x1, x2, up to xn condition on parameter theta is hard. So you always assume that these observations are independent condition on theta. Assumption. F xi condition of theta is independent of xj condition on theta. So if this is the case, I can simplify the likelihood formula. Simplification. I can write f of x1 up to xn condition on theta as multiplication of the probabilities, right? F of xi condition on theta. Make sense? Because I assume that they are conditionally independent. This is the criteria I have for maximum likelihood. I always need to maximize this term. So if you see a likelihood question, you need to find this term and try to maximize it. This is also called likelihood function. Likelihood function. Okay, any questions so far? Nothing? Okay, let's solve the question. Question number 1. Suppose we have random samples x1 up to xn, where xi is equal to 0 if a randomly selected student does not own a car, and it is equal to 1 if he owns the car. Assuming that xi's are independent Bernoulli random variables with unknown parameter p, find the maximum likelihood estimator for p. Meaning that we are trying to find the best estimation for this value p. So we are asked to use maximum likelihood estimation. If we were not asked to use such method, we should have come up with using maximum likelihood. Because of what? Because you don't see any prior distribution for p. That's the point. So in the other questions you had for MAP elements, always a prior knowledge f of theta was given for you. For example, we assume that theta is coming from normal distribution, uniform distribution. Do you recall? But now you don't have any assumptions over the distribution of p. I know p is random, but no distribution is given. So assume that this last part of the question was not given. So that's the point. Still you have to use MLE. Make sense? So question 1. We have, let's write the information we have. I know that f of f of f of xi condition on p is equal to f of xi conditional p is coming from Bernoulli distribution, right? So Bernoulli random variable, it is either equal to p or 1 minus p equal to p if he owns a car. So xi equal to 0. Xi equal to 1, right? Owns a car. Yeah, xi equal to 1. Otherwise, xi equal to 0 is equal to 1 minus p. Correct? Now, I have a piecewise function, meaning that it has two pieces. It's hard to put it in this formula. So instead, I can rewrite this function and let's rewrite it or reformulate it such that I have a function with only one term. How can we do that? I can write it is equal to p to the power of xi times 1 minus p to the power of 1 minus xi. Why this is correct? Because assume that xi is equal to 1. Then I have p to the power of 1 times 1 minus p to the power of 0. This term will be eliminated, so I have p. Also, if I have xi equal to 0, p to the power of 0 is 1, so I only have 1 minus p to the power of 1. Correct. So I rewrote this piecewise function such that I only have one term. Make sense? Okay, now let's make the likelihood function. The likelihood function is equal to multiplication of I from 1 to n of p to the power of xi, 1 minus p to the power of 1 minus xi. Why? Because I'll just follow this rule. In the maximum likelihood estimation, I always try to maximize this term, multiplication of likelihood. Now I found the likelihood for one of the xi. I need to multiply them all together to find the likelihood function. Now I need to maximize this function. Make sense? So far so good? Okay, but instead of maximizing the likelihood, it's easier for you to maximize the log likelihood instead. Let's find the reason. So generally, maximizing a function f of x is equivalent to maximizing log of f of x. Okay? Because log is increasing function. So maximizing f of x is similar to maximizing log of f of x. Now, here you have multiplication of some terms. If I want to maximize it, I need to find derivative. Derivative of multiplication of some terms is hard. Okay? But if I take log, this multiplication becomes summation. And finding the derivative will become easier. That's the point. So I try to maximize log of L instead. So let's find it. Log of L. I want to take log from this function. Okay. So here I have p to the power of x1 times p to the power of x2 times up to p to the power of xn. P, the base is common. Once they are multiplied, the exponent is summed up. So I have p to the power of summation of xi. Okay, let me first simplify it, sorry. Let me rewrite this function L. Let's see, L of p is equal to, so for now L of p, I just want to rewrite it. P to the power of summation of xi, 1 minus p to the power of, again, I have a common base, the exponent will be summed up. Right? I just rewrote it. Now I can take a log. Is it clear? Yes.
P is plain 8 again.
Yeah. So what happens here? I just rewrote this formula. What? This product is multiplication, right? So let's consider this term. What do we have? P to the power of x1 times P to the power of x2 times P to the power of x3. Once you multiply them, P, the base is common among all of them.
Oh, yeah.
So the exponent will be summed up, right? So I have P to the power of summation of exponents. Same scenario for this term as well. Okay, now, so again, I have multiplication. This is hard to find the derivative of it. Specifically, you have power, makes it more, makes it harder. So instead, we find log of L, which is equal to, so do you remember how we get log? So if I have log of variable, let me write log of alpha to the power of n is equal to n times log of alpha. So I use this property. So I take out the exponent summation of xi times log of p. Now I have multiplication of these two terms. It will be addition when you take log. Again, this exponent comes out 1 minus xi times log of 1 minus p. Okay? Clear? Any questions? You got it?
Yeah.
Yep.
I'm still just struggling to interpret the f of xi given p. So
Okay.
the problem, so
It's
given
Bernoulli, so it's either P or minus P. Yes, assuming that it's independent Bernoulli random variables with unknown parameter P. Yes.
okay, if x is equal to 1, okay.
Okay, so I have this formula. I took log, it simplified to this one. Now, what is the next step? The next step is to find the best value for P. So derivative of log of L with respect to P is equal to, I want to maximize it, so find the derivative with respect to P and put it equal to 0. Let's do. This term is a coefficient, it's constant with respect to P, so I just write it. Derivative of log of P is 1 over P. Plus, this term is constant, so I treat it as a coefficient. What about derivative of this term? Do you remember derivative of log? So if I have ln f of x, the derivative of this function is equal to f prime of x over f of x. Okay, so in this case, derivative of 1 minus p is negative 1 over 1 minus p. I put it equal to 0. Now let's solve it for p. I multiply both sides by p times 1 minus p to get 1 minus p equal to p times summation of 1 minus xi. Yes. Therefore, also for this term, I have summation of this from I from 1 to n. So summation of 1 minus xi, this 1 is constant and it is repeated n times. So this is actually equal to n minus summation of xi. Let's expand it. I have summation of xi minus p times summation of xi equal to n times p minus p times summation of xi. Summation of xi. So these two terms will cancel out, and I have p equal to summation of xi over n. So I found the best estimation for p based on the likelihood. maximum likelihood estimator. Any questions? Okay. The next question. Suppose we have random samples again, x1 up to xn, from the normal distribution with unknown parameter mu and variance sigma squared. Find the maximum likelihood estimator of mean and variance. The same thing, but now we have Gaussian distribution instead of Bernoulli. So based on the information given in the question, I know that f of xi condition on. Now xi depends on two parameters, mu and sigma squared. So f of xi condition on mu and sigma squared is equal to, they're coming from normal distribution. 1 over root of 2 pi sigma squared times e to the power of minus x minus mu to the power of 2 over 2 sigma squared. Right? Okay. So this is the likelihood function for xi given mu and sigma squared. Now, we are trying to use MLE, so I just have to form this likelihood function. So for likelihood function, I have multiplication of f of xi condition on mu and sigma squared is equal to, okay, so I need to multiply this times, let me write, it's better if I write. It's equal to I from 1 to n, 1 over 2 pi sigma squared to the power of n times e to the power of minus x pi minus mu, here I have I, to the power of 2 sigma squared. Right? So for the likelihood, I need to multiply all the likelihood functions to get this term. Or did I write anything? Okay. Now, this term is constant. It doesn't have I in it. So it's constant in this product. So I can take it out. How? I know that this term is repeated n times. So this is equal to 1 over root of 2 pi sigma squared to the power of n, because it's repeated n times. What about this term? Once I multiply all these terms together, the base is always e, and the exponent will be summed up. Similar to the previous question we had. So it will be e to the power of minus summation of xi minus mu to the power of 2 over 2 sigma squared. Make sense? You follow? Okay. Again, I have multiplication and also something in exponent of e. It's hard for me to find the derivative, but instead I take log here. Go ahead.
Aren't you summing it up? So how would you
Raised
raise the
to m, this one?
Yeah, you're summing it up.
No. This is prompt. Multiplication of these terms. Yes? Your questions answered, solved? Okay, so I take log of this function. Log of L is equal to, let's take log. Log of this term. Do you remember? Let me review. Let me review. So here, for example, if I have log of 1 over x to the power of 5, n, this is equal to log of x to the power of minus n equal to minus n times log of x, right? The same thing here. So this term can be written as 2 pi times sigma squared to the power of minus n over 2. Agree? So I just use that. I take this out. I have also multiplication here. I can write it in terms of summation. That means minus n over 2 times log of 2 pi for this term. Again, minus n over 2 times log of sigma squared for the second term. Again, we take log, the multiplication becomes summation. And this coefficient minus n over 2 will be out after log. So minus n over 2 times log of this term will be minus 1 over 2 times log of summation. Okay, this term is multiplied by e to the power of something. So I have this one plus, the multiplication becomes plus, log of this term, because we have e to the power of something. You take log, you only have the exponent, right? So it will become minus the exponent xi minus mu to the power of 2 over 2 sigma squared I from 1 to n. Yeah. Any questions? Here. Now let's find mu and sigma squared. These are the two unknown parameters, right? This is the log likelihood function. I want to find the best mu and sigma squared such that this function is maximized. So I find derivative. So in the first one, in the first step, I solve mu. So find the derivative of log likelihood with respect to mu. This is constant with respect to mu, so I have 0. Constant with respect to mu, I have 0. Now here, how can I find the derivative of this term? Let's review. If I want to find derivative of f of x to the power of n, I want to find the derivative of f of x to the power of n. This is equal to n times f prime of x times f of x to the power of n minus 1. From calculus 1. Okay, now here I have summation of some terms. I can find the derivative of each of them separately and then put the summation because I know derivative is additive. Okay, so I find the derivative of one of the terms. For example, I fix xi. So I have xi minus mu to the power of 2. Let's find the derivative by this formula. So I have 2 coming out based on the power comes out times derivative of f. Xi minus mu is your f. derivative with respect to mu is minus 1. Times f of x to the power of n minus 1. F of x, which is x minus mu to the power of 2 minus 1. Now I put the coefficient, and also I write the summation as well. Clear? Okay, now this negative and the other negative cancel out, and I have positive here. So I found the derivative of likelihood with respect to mu. I put it equal to 0 to find the best value for mu. I solve it for mu. So let's simplify. This is equal to, from this I can say this 2 and 2 will be eliminated, and I have 1 up to n xi minus mu over sigma squared equal to 0 equals, from this I know the sigma squared in the denominator is common for all of them, so I put the summation of numerator equal to 0. Based on this mu is constant in this summation, so I have n of them, right? Plus summation of xi equal to 0, therefore mu is equal to summation of xi over n. Hard?
I don't know.
We need to review.
Yeah.
Okay, so I found mu. In the next step, I need to find sigma squared. Because again, let's get back to the problem we solved. I have a normal distribution. It has two parameters, mu and sigma squared. I need to estimate both of them. So first, I found an estimation for mu. In the next step, I find an estimation for sigma squared. So I have to find the derivative of likelihood with respect to sigma squared. Correct? Okay. So again, another lesson from derivative. How can I explain it? Once you want to find the derivative of a function with respect to a variable to the power of 2. Now, we treat this variable as one variable. Don't look at it as a variable to the power of 2. For example, let's call it alpha. So whenever I see sigma squared here, I treat it as alpha. You will see what I'm saying. So this is equal to where is it? Oh, the likelihood here is here. So I need to find the derivative of likelihood with respect to sigma squared. The first term is constant. It doesn't have any sigma squared in it. So 0 plus. What about the second term? The coefficient is minus n over 2. And I have log of sigma squared. Now, here's the point. I treat this sigma squared as one variable. For example, alpha. Now, I'm finding the derivative of likelihood with respect to alpha. Alpha shows up here. What is the derivative of log of alpha? 1 over alpha. In this case, alpha is sigma squared, so it is equal to 1 over sigma squared. Okay, because assume that you are finding the derivative with respect to alpha. Here is log of alpha. It becomes 1 over alpha. Alpha is sigma squared. Okay, what about the next term? The next term is minus. So this 2 sigma squared shows up here. Let me the other terms are actually coefficients for it. This xi minus mu to the power of 2 over 2, we can treat it as a coefficient. So let me write it. I have a coefficient here which is minus xi minus mu to the power of 2 over 2. This is a coefficient. Now, what is left is 1 over sigma squared. I need to find the derivative of 1 over sigma squared. What is the derivative of 1 over sigma squared? Similar approach. I treat the sigma squared as one variable. Let's call it alpha. What is the derivative of 1 over alpha? It is minus 1 over alpha squared. Okay? So minus 1 over alpha squared, which is sigma squared to the power of 4. Confusing? Good. Okay, so I put this one equal to 0. Let's solve it. So I put that one on the other side. I have 2 cancel out, so I have n times sigma squared equal to summation of xi minus mu to the power of 2. Therefore, I have sigma squared equal to summation of xi minus mu to the power of 2 over n. It makes sense because previously you calculated the sample variance. It has this form, right? And we got the same formula here as well. Makes sense. And yeah, go ahead.
When you were finding the derivative of the mu, in your second step, the line underneath, where did the sigma squared come in?
Oh, okay. So in this summation, the denominator is constant. So in the numerator, I have summation of this term, but the denominator is constant. Then put this fraction equal to 0. Then the numerator should be 0. You don't care about the denominator anymore. Did you get what I said? If it is hard to understand, just multiply both sides by the sigma squared. This will be eliminated. 0 times sigma squared. Okay. Question number 3. Suppose that we have random variable, random samples coming, this time from Poisson distribution. So again, solving the same question, assuming that f of x condition on this time lambda coming from Poisson distribution. Question number 3. Okay, f of xi condition on lambda is equal to, what was the formula for Poisson? I forgot. E to the power of, what was it? Xi. Help me out. Let me see. I have it here. Yeah, here it is. Lambda to the power of x over xi factorial e to the power of minus lambda. Okay, so again, what's the meaning of this notation? It means that if you fix the variable, the unknown variable lambda, then you know that xi has a Poisson distribution. So you need to fix it. Why? Because lambda itself is a random variable, unknown random variable. So you cannot find the distribution of xi itself. You should make it conditional to get Poisson distribution. That's the point. Similar to the other question we solved. I always make it conditional. In the first question, condition on P. Then I had Bernoulli. In the second question, I made it conditional on mu and sigma squared. Then I had Gaussian. And same scenario here. Okay, so what is the likelihood function. Likelihood function is the multiplication of these terms. Lambda to the power of xi over xi factorial e to the power of minus lambda. Which is equal to lambda to the power of xi. This lambda, the base, is constant, so the power, the exponent, will sum up to summation of xi. Denominator, I cannot do anything with the denominator, so I just repeat it. x1 factorial, x2 factorial, up to xn factorial. And here I have e to the power of minus lambda n times multiplied to itself. So I have e to the power e to the power of minus lambda times e to the power of minus lambda n times, giving you e to the power of minus n times lambda. Make sense? So this is the likelihood. As usual, we find the likelihood instead, and then we find the derivative. Let's take log. This is equal to log of lambda to the power of xi is equal to summation of xi times log of lambda. And also, the denominator I have minus log of. Again, the same term, I cannot simplify anything here. Log of e to the power of minus n lambda will become minus n lambda. Any questions about this? The calculation for log, I can review if you have any questions. Okay. Not more question? So, as usual, I find the derivative of likelihood with respect to my parameter, which is lambda in this case. The derivative of this term. This summation of xi is a coefficient because it is constant with respect to lambda. So I just repeat it. Summation of xi times. What is the derivative of log of lambda? It is 1 over lambda. And this whole term, log of multiplication of factorial, is constant with respect to lambda, so the derivative of it is equal to 0, plus 0. Plus. Derivative of minus n lambda is minus n. Let's put it equal to 0. So it turns out lambda is equal to summation of xi over n. I found the best estimation for parameter lambda. Meaning that we just sum of the observations divided by the number of them to get the best value for lambda. Now let's solve a question. Numerical. Okay, so question 3.2. The following data are observed frequencies of the occurrence of domestic accidents. We have 647 data as follows. We are trying to estimate the parameter of lambda. We assume that these data are coming from Poisson distribution because it's the second part of the question number 3. 3.1 is the second part. So I assume that the observations are from the Poisson distribution. I used the answer I found for lambda before in the previous part, and I estimate the value for lambda. So this data is coming from Poisson distribution. If I want to find the best value for lambda, I just follow this rule. Question 3.2. Lambda is equal to summation of xi. Summation of xi, let's find it. 0 times 447 plus 1 times 132. Oh, up to the last one, which is 5 times 2. And how many of them do I have? 647. Right? N goes at the denominator, and in the numerator I found the summation of data. Clear? This is equal to, final answer. Zero four six five. 0465. And that's it. Any questions? So we solved 3 similar questions from maximum likelihood estimation. Each of them had different assumption over the variable xi. One of them Bernoulli, the other one Gaussian, the third one was Poisson. The only thing matters here is that how you can distinguish between MLE elements and MLE. Again, let me recap. In MLE, you don't need to know the prior distribution for theta. You see, in this question, we didn't know that. For example, in Poisson, lambda coming from which distribution? We don't know that. So the only option I have is to find the maximum likelihood. You can no longer use map nor LMS. That's the point. Any questions?